Okay, let's continue. So from this input matrix X and output matrix output vector Y, so okay, we can represent this X variable Xi in this case here, right? So it can be represented by n+1 vector, and with this variable like this, the input variable looks like this. So the input vector will be the size looks like this, m times n+1 here. So m is the number of samples and is number of features. In this case, the number of features will be the what? 4, right? And the number of samples will be the sorry about that. So this is the least scale solution. So yeah. So where is that? Yeah. So if we represent this linear system with respect to the W, it will be represent XW is equal to Y, and we want to find this W term. And how can we do this? X transpose X W X transpose Y like this. And how can we estimate this? We can compute the inverse of this one. So it will be X transpose X inverse X transpose Y, something like this. So this is called the least scale solution of with the input matrix X, output matrix Y. So in here, this term is called the gram matrix. This term. This term is the inverse of the matrix. This one. Okay. So this is the definition of the normal equation. Then okay, let's compare the gradient descent with the normal equation. What is the gradient descent? This is the gradient descent. Gradient descent use the iterative solution to find the use this one. Okay. Gradient descent use the iterative solution. So it updates the values with the learning rate alpha. So it need many iteration, but it works well when n is very large. Comparing to this, the normal equation, we don't need to the alpha value. I mean the learning rate. We don't need to the iteration solver, but we need to solve this gram matrix and inverse of gram matrix, and it will be very slow if n is very large. What does that mean? So when it's just think about this case, from this example, m is equal to 4 and n is equal to 4, so it means that 5, right? So in this case, X transpose X will be the what? X transpose X will be the 5 times 5 by 5, right? Actually, this equation is not so big relatively, but if we think about the n is number of n means the number of features, right? So we could relate it to here. N is equal to 100 or 1000, something like this. The compute the inverse of this large scale matrix will be the really slow. The So in this case, compute the order of the computing this equation will be the order n square. It will be very slow, right? So, but if we use the gradient descent algorithm, let's say n is equal to something like this. Even for such a large values, the gradient descent works well. And gradient descent don't need to any constraint that the equation should be convex or something like this, but normal equation, the condition of the normal equation is should be the original loss function should be convex. So it is the difference between gradient descent to normal equation. So actually, the most motion learning technique based on the gradient descent and use the gradient descent to solve the their own loss function. Okay. And there are also another problem. What if the this gram matrix is length deficient? I mean, it means that it is not non-invertible. For example, if some kinds of features are linear dependent, or there are too many features. In this case, we can use the sum feature, delete some feature, or we can use the regularization. We will discuss this the next week's lecture. Anyway, so in this case, it's really hard to find the solution by using the normal equation. So there are some kinds of technique to solve the normal equation, even in case of the non-invertible case, but it's really hard to, and it's more complicated than the gradient descent algorithm. So yeah. Okay, let's summarize the linear regression. We studied the three types of methods to solve the linear regression. The first one is the grid search, and second one is iterative optimization algorithm, such as the gradient descent, and third one is the least square, a closed form solution for the MSE problem. So actually this method just used for the very specific case, right? So I would say this gradient descent method is the very popular optimization technique to solve the linear regression problem. Okay, even for linear regression problem, we can also solve the classification problem using the gradient descent, which will be discussed from now on. Okay, let's go back. Move on to the classification problem. From last week to the previous slide, we have learned the regression problem. Now we will talk about the classification problem. What is a classification problem? If you understand what is regression correctly, classification is not so difficult. Classification is very related to the regression problem. Classification is also relate the input variable, let's say x, to the output variable, let's say y. But comparing to the regression problem, the output variable y can only take a discrete value. What is the discrete value? Discrete value something like 0, 1, 2, 100, something like this. We cannot use the 1.2 or 0.05, something like this. We cannot use that because it's not a discrete value. Okay? Actually, we can use this value in some case. If we just define our discrete case as looks like this, but generally we can say that the discrete values is an integer. Okay? Anyway, so we can say that the output y only take the discrete value, and y is the categorical variable. Okay. So for example, there are several kinds of classification problems. First one is the spam and not spam case. For arbitrary email, we can determine this email is the spam or not by using the classification machine or classification method, or there are another example, pollutant yes or not, and tumor. In this case, we can determine from some signal what this is malignant or benign. So from all of this case, the Y can be the two cases, spam or not, yes or no, malignant or not. Okay. So actually, this is the two class classification problem. Okay, this is a two class classification problem. The class will be the 0 or 1. 0 class means the negative class, and 1 class means the positive class, like this. So this is the general classification problem setting. So yeah, let's see the example. What is the classification problem? Okay, so let's think about the expectation of the tumor, this case. Okay, so let's say we have the training sample like this. So there are 8 kinds of training samples, right? 8 kinds of training sample. The input of the training sample will be the tumor size, just the size of the tumor, and the output of the training sample will be 0 or 1. Okay, 0 means it's not a malignant, but 1 means it was the malignant. So this is the classification setting. Then how can we develop our machine to decide this new sample with this tumor size? How can we determine this sample is the malignant or not? In the last lecture, we have learned the regression problem. So by using the linear regression problem or linear regression equation, we can learn the the linear regression mapping function like this. Okay, so in here, from this sample, if we just think about this Y is the parameter of the sample, we can learn the mapping function. Looks like this. It was something like this, right? If we think about X is the input variable, right? So, but as you can see here, in this case, we can say that, okay, with this tumor side, it should be here. So it means that it is probably similar to the malignant case, right? But it seems like the reasonable, but if we think about there are this case with a really large tumor site, it was the class 1, then in case if we just using the linear regression linear regression setting, we should find the straight line will be looks like this. Why? Because this is the very large outlier. As we discussed previously, using the lowest cost function, we can deal with these. Maybe we can deal with this one, but generally, the linear regression problem is really sensitive to the outlier, and the lowest cost function is need a very high computational cost. Okay. So what do you want to do? What do you want to do in classification setting? We want to find the stress. We want to find a way to threshold the classifier output fwx at the 0.5. Let's say 0.5 here. Okay, so if we define the mapping regression classification mapping function with some kind of way, let's say this mapping function is larger than the 0.5, we can predict the output class is equal to 1. Otherwise, we can determine the output class y is equal to 0. The question is, how can we develop this kind of the algorithm to classify the output of the mapping function? Okay, so this is the goal of the classification problem. Okay, anyways, the classification is in the classification we have to find the output y is equal to 0 or y is equal to 1. So actually this mapping function can be larger than 1 or lesser than 0, but in generally, to make the computation tractable, we just assume that or use that mapping function looks like this. So we want to formulate our mapping function is larger than 0 and lesser than 1. So if we use the mapping function looks like this, we can say that this is the logistic regression. This is for the classification problem. So we can say that we using this kind of mapping function, we can solve the classification problem using the logistic regression function. Some of you are confusing with the linear regression problem, right? So actually linear regression and logistic regression are definitely different. This is for regression, this is for classification, but they use the same terminology because the goal of the classification is similar, because each relate the input variable to output variable. So that's why it is called the logistic regression. Okay. Anyway, so for classification problem, we should learn what is logistic regression. Okay. So first of all, we have to define the classification function or hypothesis or mapping function, something like this. So comparing to the linear regression model, we have the additional constraint like this. Our mapping function should be larger than 0, less than 1, right? So for this one, we introduced this nonlinear function z. The shape of z. You can find the shape of this function easily. Looks like, let's say this is the z. Looks like this. Okay, let's see the example. Yeah, this should be z. What does that mean? If we have the z value larger than 0, the output of the g of z should be larger than 0.5. But if the 0 is negative, the g of z should be less than 0.5. So using this function, we can satisfy this constraint. Then we can also determine z as a just linear equation with the with the network, not network, the machine parameter W with the input vector X. Okay, so actually it is the similar to the linear regression problem, right? The main difference is we introduced this nonlinear function to satisfy this constraint. So finally, we can define our logistic regression model. It looks like this: 1 over 1 plus exponential minus W transpose X. It's like this. So this is our logistic regression model, because some of you have a question why we have to use this regression model. Because we can make another nonlinear function or the linear function that satisfy this one. Then why we should use this one? Right, you're right. Actually, we can use any kind of the nonlinear function that satisfy this constraint for the regression problem. But from the many literature, they found that this form of logistic regression is the most powerful representation than the other nonlinear function. So that's why we use this nonlinear function to classification problem. So this mapping function is also called the sigmoid function or the logistic function. Anyway, from now on we can use this mapping function for the classification problem. Okay, so let's say fw of x. What is the meaning of the fwx? We can say that this is the probability that y is equal to 1 on input vector x. Okay, let's see the example. Okay, we have a input variable x1 and x0 and x1. In the multi-variable linear scale case, we assume that x0 is just equal to 1, right? So x0 will be the 1 and x1 will be the tumor size in this case. Okay, in this case, anyway, we found some variable w, and we have a classifier. With this classifier, from this x value, we found the output of this mapping function was the 0.7. Then what does that mean? We can tell the patient that the 70% chance of the tumor being malignant. So it means that we can think that this is the kind of the probability that y is equal to 1 in two variable cases. Okay, in two variable classification case. Okay, so for formally, this is the logistic regression mapping function. Here, W was the, what was that? W was the parameter, right? And X was the input, right? So in this case, we can represent this mapping function. Looks like this. So it means that this is the parameter that y is equal to 1 given input X parameterized by W. Okay? So it will be learnable parameter, right? And it will be input feature, right? So what does that mean? So if we train this machine, classification machine, and so found the W value, and if we given by input variable feature, we can determine the probability that y is equal to 1. Okay? So What does that mean? And because we assume that there are two class cases, the probability of the y is equal to 1 and probability of the y is equal to 0, the summation of this probability should be 1. The summation of these two probabilities is equal to 1. Because there are only two kinds of cases. What does that mean? If the probability of y is equal to 1 is 0.7, then we can say that there are 30% of chance of tumor being non-malignant, right?